All right, you guys. April 27th, we're going to do section 5.6, last section in chapter 5. And after this, you guys, we've only got a couple chapters left. And each of those chapters only has 4 sections. So we're kind of on the home stretch here. The last section here is going to be dealing with finance, different formulas. It really is just kind of a plug and chug section. So if you guys write down the formulas and you understand the parts, we'll be good to go. So simple interest is this formula here. Interest equals principal, which is the amount that you invest, times the interest rate, which is always as a decimal, so 5% would be 0.05, and time, which is in years. So 6 months would be half a year, for instance. And so we're going to be doing some problems where we're calculating simple interest. And then this is just the total accumulated for the period. So if you were to take the interest that you made plus the original principal, that's how much money you'd have total, including the original investment. Okay? So if we take a look at an example here, many finance companies offer what have become known as payday loans, a small $50 loan to help people get by until payday, usually no longer than 2 weeks. So if the cost of a service is $12.50, determine the annual rate of interest charged by these companies. This is going to surprise you, I think, a little bit. So we've got interest equals principal times rate times time. Okay? So the $12.50 is what they're charging. So this is going to be the interest. The principal, that's that $50 loan that we got. The rate, we don't know. And then the time, remember it's in terms of years, so 2 weeks is 2 weeks out of 52 weeks, or 1/26th of a year. Okay? And then you've got some algebra to do, 50 times 1/26th, and you have to divide that into 1250. And so when you solve for R here, you get 6.5, which if you make that a percent, is 650% annual interest. So when you look at that, is a payday loan really a good idea? Probably not. Okay, it gets you through for a couple of weeks, but you're paying an exorbitant amount of interest on something like that. So just understanding the parts: interest, principal, rate, and time, and putting the numbers into the right spot. Okay, interest compounded annually. So if I compound it or I calculate the interest once a year, then my formula looks like this: principal times 1 plus the rate. So 1 plus, 0.05 if it was 5%, raised to the t the number of years. Okay? If an accumulated value A is desired after t years and the money is deposited at an interest rate R compounded yearly, the present value is this. And that's really just solving for the p, you guys. That's no big deal. Okay? So this is for compounded annually, once a year. After being promised an 8% return compounded yearly, Steve decides to invest $1,000 in his friend's startup company. How long will it take for the money to double? Okay, so A equals P, and then 1 plus R to the T. This is the formula we're using. Okay, so if he invested $1,000, when it doubles, it will be worth $2,000. Okay, so we're over here. And then we've got 1 plus the rate. Remember, we write it as a decimal, 0.08, raised to the t. Okay? So, a little bit of math. I'm going to have to divide by 1,000. So now I have 2 equals 1.08 to the t. And now's when I got to use the logarithmic stuff that I've learned here. Okay? So, because I've got an exponent that's a variable, I'm going to take the log of both sides. So on this side, the ln of 2, and on this side, the power comes out in front, like so. Okay, divide both sides by ln of 1.08, and I get t to be about 9 years. So if you put $1,000 into an investment that gives you 8% compounded yearly, it will take you 9 years for that to double. Okay? All right, now, what if I want to compound it more times? Okay, very similar formula. R is still the rate, P is still the principal, N is the number of compounding periods. So if I said compounded monthly, N would be 12. Okay, so just a new formula, you gotta make sure you have this in your notes. We'll be working through this example here. All right, so Macklin won $150,000 in the Missouri lottery and decides to invest the money for retirement 20 years. Of all options available here, which one will produce the most money for retirement? Okay, so I just need to take that formula. Let's just remind ourselves what that formula is here. Okay, and I'm gonna go ahead and put it in there. So for A, a certificate of deposit paying 5.4% compounded yearly. Okay, so we've got 150,000. 1 plus 0.054 compounded yearly, so over 1 for 20 years, so to the 20 times 1. Okay, so if I work that out, and again, this is just a matter of putting it into your calculator at this point. Grab your calculator, put it in. I get 429,440 and 97 cents. Okay, so that would be if I compounded it yearly at 5.4%. Okay, the second one, a money market certificate paying 5.35% compounded semi-annually, which means twice a year. Okay, so here I'm going to go principal, your 150,000. 1 plus 0.0535 compounded semi-annually, so divided by 2, raised to the 20 for the number of years times 2, which is n. Okay, so I go ahead and put that in, and I get 431,200.96. Okay, so that one's a little better deal. We'll see if that one hangs on to be the winner or not. A bank account paying 5.25% compounded quarterly. So your 150,000, 1 plus 0.0525. Quarterly is 4 times a year, so divided by 4, raised to the 20 times 4. Okay, I work that out, and I get 425,729.59. Okay, and then this last one, paying 5.2% compounded daily. Okay, so your 150,000. 0.052 compounded daily, 365 days in a year, raised to the 20 times 365. Okay, you'd think compounding it that many times would make a big difference, but 424,351.12. Okay, just a matter of getting the right numbers in the right spot and working this out. So here, which one's the better deal? E is the better deal. It gives you the most, 431,000. Okay. Yeah. So just make sure you have that formula in your notes and practice it as you work through these. Okay. All right. One more. What if I can compound continuously? So it's constantly calculating the compound interest and working it from there. This formula, P is still principal. E is that natural number E. Raised to the RT, where rate is the interest rate and T is time. So, but this is just for compounding continuously. All right, so Jamin has $10,000 to invest and wants to have at least $25,000 in the account in 10 years for his daughter's college education fund. If the account pays interest compounded continuously, what interest rate is required? Okay, so here's our formula as a reminder. Okay, so I want my future value, I want it to be $25,000, and I'm starting with 10,000 times E to the R times, and I have 10 years to do it in. So there's my formula, okay? The rest of what I have to do here is algebra. So I'm going to try to get E by itself. I'm going to divide by 10,000. And to undo an exponential, I need to take a logarithm. And since I've got base E, natural log will undo that. So I've got the natural log of 2.5 equals 10 times r, because the natural log and the E are inverses. They get rid of each other. So now if I divide by 10, so the ln of 2.5 divided by 10, I get 0.0916, which would be 9.16%. Okay? So that would be the interest rate that you would need to reach your goal of 25,000. Okay? All right, accumulated value. So this one's a little bit different. This is an annuity, so this is a situation where you're putting money in periodically. So like every month. I invest in my college, my son and daughter's college education. I put $50 in every month. That's an annuity. Okay, so if a periodic payment P is deposited, so that would be the $50 that I put every month. N times per year, so if it was monthly, N would be 12, etc. At an annual interest rate R, with interest compounded N times per year, the accumulated value is this formula. P over R, 1 plus R to the N minus 1, where big R is that R over N, and big N is N times T. Okay, so you got to have that formula written down, and then we will crank out an example for you here. All right, so it says, since he was a young child, Fitsumanu's parents have been depositing $50 each month into an annuity that pays 6% annually and is compounded monthly. If the account is now worth $98.75, how long has it been open? All right, so our formula like so. R was equal to R over N, which in this case is 0.06 compounded monthly over 12. Okay, and that gives you 0.005. Okay, and big N compounded monthly would be 12T. Okay, so those are the things I would start with, and then I can start putting numbers into the formula. Okay, so if the account is now worth $98.75, that's the A. Okay, P, that's 50. I'm putting 50 into the account over big R, which we said was 0.005. Okay, and then I have 1 plus 0.005. That's that big R again. Raised to the 12t, that was our big N, minus 1. Okay, and I'm supposed to solve for t. So my job is to isolate that exponential so that I can use some logarithms and solve here. Okay, so the very first thing I'm going to do is take 50 divided by 0.005 and then divide it into the 98.75. Okay, and I get 0.9875 on this side. And then on this side, I'm left with the 1 plus 0.005 to the 12t minus 1. Well, of course, I'm going to add 1 then. So now I have 1.9875 equals 1 plus 0.005 to the 12t. Okay. Now I've got an exponential, so I need to undo this with a logarithm. So I'm going to take the log of both sides. Your exponent goes out in the front, so 12t ln of 1.005. Okay, and now if I want t by itself, I could divide both sides by 12 times ln of 1.005, and I get t to be about 11.48 years. Okay, so in that situation, if I am able to put $50 into an account every month for 11.48 years, if I get 6% interest, we'll have $98.75 in that account. Okay, so that's an example of how that formula is going to work. All right, Sheila's determined to stay out of debt and decides to save $20,000 to pay cash for a new car in 4 years. The best investment vehicle she can find pays 9% compounded monthly. If $300 is the most she can invest each month, can she meet her new goal? Okay? Again, that's that formula we just looked at. Okay? So that's that P over R, 1 plus R to the N minus 1. Okay? In this scenario, our interest rate's 9%, and N compounded monthly is still 12. Okay, that gives me 0.0075. And big N is going to be little n times T, which is 4 years. This is a 4-year goal. Okay, so that's just going to be 48. And this one's easier. I don't have a lot of algebra to do. I'm just going to try to solve this. We're going to try to see if we can get to our $20,000 goal. So we're putting in $300 a month over R, which is 0.0075. And then we have 1 plus 0.0075. All right, guys. Well, sorry about that. I got cut off in the middle of doing example 6. The PowerPoint kind of locked up and wouldn't let me write on the board. So rebooted the computer, giving it a second shot. So one more time, Sheila determined to stay out of debt and decides to save $20,000 to pay cash for a new car in 4 years. The best investment vehicle she can find pays 9% compounded monthly. If $300 is the most she can invest each month, can she meet her 4-year goal? Okay, so there's our formula for an annuity. Capital R, remember, is the interest rate, 9%, divided by the number of times compounded in a year. Monthly means 12. So our big R is going to be 0.0075. Big N is the number of times compounded, which was 12 times the number of years, 4. So then I'm going to just plug this into this formula here. So I've got P, which was 300, over R, which was 0.0075. Then I get 1 plus 0.0075 raised to the N, which was 48, minus 1. Okay? So there's my formula. And the right side of the equal sign is just numbers, you guys. So I should be able to type all of that into the calculator. Okay? When I do that, I get 17,256.21. Okay, so can she reach her goal in 4 years? Well, her goal was $20,000. We only made 17,000. So I would say no. The other way you could do this is we could have put a 20,000 in for A and solved for T to see if 4 years was enough, and it's not. Okay, so that's another way. I think that's how the book handles it. Okay, so let's move on. We got a couple more examples. Exponential growth and decay looks like this. Q of T equals Q sub 0, meaning the initial amount, whether it's a population or something like that. E to the RT. If it's decay, it's just negative RT for that exponent, okay? So keep that formula in mind as we work through the next example. Because fruit flies multiply very quickly, they're often used in studies of genetics. Given the necessary space and food supply, a certain population of fruit flies is known to double every 12 days. If there are 100 fruit flies to begin with, find the growth rate R. So let's start there, okay? So I'm going to write this formula up here again. Q of T equals Q sub 0 E to the RT. That's kind of what we're dealing with here. We're going to try to find this R. So for part A, okay, we started with 100 fruit flies and we wanted to double. So we're going to get to 200. We started with 100 E, and we're doing this for 12 days. So 12 times R. And so the only thing missing is the R. And so I have a little bit of algebra to do. I'm going to divide by 100. Because I've got an exponential, I need a logarithm to undo that. So I'm going to take the natural log of both sides. When you take the natural log of E, it undoes it. So then I'm left with just 12R. And so if I divide by 12, ln of 2 divided by 12, I get 0.058. okay, or about 5.8%. That is going to be your growth rate, okay? And then for B, the number of days until the population reaches 2,000. Okay, now that I have my growth rate, I want to get to 2,000. Okay, so that's going to be this side. I'm starting at 100, and the growth rate's at 0.058, and this time the t is unknown. Okay, the algebra is going to be quite similar to what I did up here, except I'm solving for t instead of r this time. So I divide by 100, now I get 20. I have an exponential, so I need a logarithm to undo that. So this side's going to be the log of 20, and on this side I'm going to get 0.058t. And if I divide both sides by that 0.058, I get t to be 51.86. Okay? So that's how you can do an exponential growth problem. And part B, because of agriculture and agricultural encroachment on its limited habitat, the Cross River gorilla has become Africa's most endangered ape, with only 250 or so left in the wild in the year 2012. Suppose scientists expect that if the population drops below 50 gorillas, the situation will become irreversible and extinction inevitable. If the population continues to decrease at a rate of 10% per year, so exponential decay this time, how much time is left to try and correct the problem? Okay, so I'm going to use that same formula, you guys, except we're going to see how long it takes to get to 50. That's our crucial number. We're starting at 250. E, our rate is going to be negative 0.1, and then times t. So I don't know how long that's going to take. I just have some algebra to do to solve it. So I'm going to divide by 250. Okay, and then I'm going to take the log of both sides so that I can undo that e. So the ln of 0.2 equals negative 0.1t. Divide both sides by negative 0.1, and I get t is about 16.1 years. So if nothing else is done, those animals will approach extinction in 16.1 years. Okay? So the only difference between growth and decay is decay, you've got to have a negative up there for your rate, and you've got to be careful of that. Okay? All right, so if I'm dealing with radioactive rate of decay, and we talk about half-life, okay, if H represents the half-life of a radioactive substance, then the nominal rate of decay is the ln of 2 over that half-life. So when we talk about exponential decay, the same formula applies that we used before, but my growth rate will be calculated using that formula. Okay, so the radioactive element potassium-42 is often used in biological experiments since it has a half-life of only about 12.4 hours. Meaning it'll be have half the mass it did before in 12.4 hours. How much of a 5-gram sample will remain after 18 hours and 45 minutes? Okay, so the first thing I need to figure out is what my rate is going to be. And we said that that would be the ln of 2 divided by the half-life, which in this case was 12.4. Okay, and so I get 0.056 for that. Now I can go and apply that to my exponential growth or decay model. Okay, so Q of t is going to equal the initial amount, 5-gram sample, e to the rate, which is going to be negative 0.056, times time. 18 hours and 45 minutes is 18.75 hours. Okay? Well, the right side of the equal sign is just numbers, you guys. I don't have to solve for a variable. I don't have variables there. So if I do that, I'm left with 1.75 grams. Okay? So in order to use this one, I had to first find my rate, which was that ln of 2 over the half-life, and then I could apply it to my exponential decay formula. All right? Okay, and so again, look online when you look at these examples. I'm going to do a lot less problems. It says 5 through 43 odd. I'm probably going to do something like 5 through 63 every other odd. Okay? So keep that in mind. Don't do more than you have to do. All right, you guys? Good luck.